Now the statement already written on,
Yeah, okay, yeah.
and then we observed that this one was pointed, needed the zero object, this one needs the zero object, this one also needs the zero object, whereas this one and this one doesn't need the zero object. Okay, now let me go back again towards this change of basis, because this is going to come to us again and again. Change of basis functor. So what is it? Suppose if we have a morphism P, we have a point over B, then we pull back X, so this is XP as I usually write, and this is Px, and then I know that there is also this morphism which is 1, that means E is going to be E, there's identity of E, or let me write it in the other way as I usually write, as E itself, and this thing going to X is SP. Okay? And if we had another such thing over here, and say, or let me put this as X prime. Then we have the same story. This one is obstructing us. And if we had, remember, a map between points is a map which makes both these triangles to commute. And so the presence of this map forces this map here. So that is usually written as 1 cross F. So we have this functor P star. If we look into points over B of A to points over E of A. Okay? So it is taking this X, XS, remember that's how we denoted it, that is going to, so that is XP, and this is ESP, and what is that?
No, that's what I said.
So this is 1 cross F. Okay? So this is the change of basis functor, and we have shown that regarding this, we have also shown that there is this big category of points over A, and we can forget the domain, so we get the codomain. If we go to the codomain, say delta 1, this is a fibration. This is a fibration, and the fibers of this is precisely this category of points over P. Okay? The fibers are precisely this. Furthermore, there is something more to be added over here, that this is also a pullback. So this also needs to be seen. If you look into this Px and what is it, X and S, so this is E, and this is your ESP. Okay? So this diagram commutes, and if you have remembered this one, so this is UV. Having this UV actually means that PU is equal to XV, right? And if you have a W over here, if you have a W over here, such that SW is equal to Px of UV means V, so this means XSW is equal to XV, which is PU, right? So this means W, XS is 1, this is equal to PU, so this forces, if you write this map U, okay? So SPU is SW and SW is V, so this part is, so this diagram commutes. So this part is also a pullback. So in the pullback of points, this P is also the pullback. So you can see this is a pullback from both ways. You see? This is Px is the pullback of P along X, and P is the pullback of Px along S. Okay? So it's something interesting kind of a picture here. Okay? Now another thing needs to be, I need to look into, so suppose if you take this you have this 0, okay? Now this is the unique map, and if this is the unique map, I don't remember how I started denoting it, but let's say ZB. Oh, it should be like this, 0, it's from B, so something like this. Now if you, no, let me write it like this, 0B. So what is this? I want to look into this. Now what are the points over here? Say, there's no question, right? There is only one way that you can come in and one way that you can go, because it's a zero object.
Yes.
And since this is the terminal, this is nothing else but something like your B cross X, right? And this is the projection, and then this is again B, and this one being the zero map from B to X, right?
Yes.
And this is the other projection. So you see 0 star B is essentially nothing else. So what is your 0 star B doing? It is taking X to B cross X, right? So essentially we can think of this as this functor. Okay? So that's this functor. So now let's come back to one of these issues. So do you have all these things written down? It would be better if you could have it beside you. Done?
Yes.
Okay. Now the first thing, this 2 out of 3, the simple things, we know that if the left and the right, hello, yes?
Hello?
Did someone tell something?
No.
Okay.
Both sides.
Okay. So if both these are pullbacks, then the outer one is a pullback. That's already known, right? Everything. Every time. If the right hand square is a pullback and the outer square is a pullback, then the left hand square is always a pullback.
Yes.
That's also trivial. So this is actually saying this middle one is obviously I need to say the middle one is a split. So the middle is a split AP. So this is splitting it, all right? Now, so what is this? This is actually saying if the left hand and the outer squares are pullback, implies the right hand square is pullback. Okay?
Yes.
Now let's see, as I told you earlier, that the kernel, what is the kernel? Let's look into the kernel of a map. So I have this map X Fy, and I think this one should be actually done like this. So it should be some B0, okay, because this one I will denote it by this unique map is 0y. So this is exactly the kernel of F. Right? This is the unique map, and this is the kernel of F. Right?
Yes.
this is a pullback. So the kernel of f is nothing else but this pullback. Okay? Now,
obviously in a pointed category. Yeah?
yes, obviously. So, so what is 0 y star? 0 y star, so it will take a point, and it will just take it to the kernel of that point, right? Points over y, and it will take it to the kernel. Remember, the point was this epimorphism, that was the, right? The other one, yeah, kernel of, if we say that. Okay? Okay?
Yes.
So it gives rise to the kernel functor. So this is nothing else but the kernel functor. Right?
Yes.
Now the short 5 lemma. So what is the kernel functor? Kernel functor would be, so if I denote it by this, so what is the kernel functor? So it is actually the kernel functor restricted over to the points. Kernel functor gets defined for much general things. So it is from, kernel functor is actually from this comma bundles over y to bundles over y to a. So this one takes xf to the kernel of f. Okay? So the kernel so this one is therefore the inclusion or the kernel functor restricted to the points over y. Okay? Now what is the short 5 lemma? The short 5 lemma it says that suppose you take a map like this, say y, x, v, and you take the kernel. Okay, so we have this diagram, this commutative diagram. The short 5 lemma says u and v is iso, implies w is iso. Okay,
You're not putting those zeros objects, or they're not important.
which one?
The zero object on that diagram that you're not putting.
I didn't put it. Yes, you're right, I didn't put it. You should actually put this 0. And so on, right?
Yeah.
I didn't place them because it is enough. this is redundant because I have already defined the kernel. We know that the kernel is the pullback and so on and so forth.
Okay.
Yeah. So essentially, you put this or not, whatever it is, you are going to say that the short 5 lemma is a statement like this, that whenever U and V are isomorphisms, W is an isomorphism. Right?
Yes.
So, what does it say? What does it say? It says, so let's try and see. What are we doing over here? It says if you look into, okay, let's try and see. I am trying to say that short 5 lemma is essentially saying that the kernel functor reflects isomorphisms. Okay?
Okay.
Now, how do I, now what is this kernel functor? This one, let me define. I am trying to make it a bit larger now. So I take the category of arrows and I take, so I have an arrow X. I'm referring to this diagram, okay? I am taking this Kx, okay? And I am saying that here is this arrow Y, I am taking it to the kernel of Y. Now X to Y, this is this WV, okay?
Oh, yeah.
Okay? Now you see, given this W and V, this U is immediate. Why? Because you told me this is commutative. Why am I saying so? This is immediate. Why should there exist? Because from kernel of X, why? Because I can see from here that Y W kernel of X, this is Vx kernel of X, which is 0. So this map is 0, right?
Yes.
But this is the universal one, so there must exist a unique such thing. So the moment I give you this part becomes uniquely determined. So this tells us there exists a unique U such that Wkx is equal to Ky. Okay?
Okay.
Well, I started off with a commutative diagram as above, but I am saying if you look at it in this way, from WV, this U is uniquely determined. Okay? So this, since it is uniquely determined, this helps me to define this functor. Okay? And that is what I am saying the kernel functor. Let me write it like this. Now what does it mean kernel functor is reflecting iso? Kernel functor reflects iso statement means whenever U is iso, WV is iso. Okay? And that is exactly saying this. You know that A alpha implies beta and gamma. This statement is same as saying alpha and beta implies gamma, right?
Yeah.
So from this equivalence, this is exactly saying this thing. So this is same as, so this proves this equivalence. Right?
Okay.
So what I'm saying is this fact is equivalent to kernel functor reflecting isomorphisms. So therefore this fact is something very, very similar. You are taking the kernel of F, you are taking the kernel of G, with the only thing is, with the only extra condition that instead of taking any arbitrary, you are restricting that kernel functor to points, right? So we can definitely therefore say that this is a case of split short 5. This is a case of short 5 lemma. So we use the word to say so this to mean that the short 5 lemma is actually restricted to the category of points.
Okay.
All right. So hence, so it is just the and therefore this is actually we just saw that this is nothing else but the kernel functor again, right? So when you are saying that kernel functor for every object B, this one reflects isomorphisms, and you are saying this, so this observation already proves this equivalence. Okay? Clear?
Yes.
Okay. So now, and obviously as I have already told, this part C is the special case of F, right? It is the I'm sorry. If you take this one, this F and SF, and you're taking this, because what is KF? What is KF? It is the pullback of F along this pullback, right? So you're trying to pull this one back along this, so that's when you'll get KF over here. So if I write like this, so if this were like and you pull it back So this is your xb, and you pull it back, right? Then what you get over here is kf, and this is your sf, right?
Yes.
So you see that A is a special case of this, right?
Mm-hmm.
So A is a special case of F. Okay? A is a special case of F. Alright. Now let's come to another thing which this is something which is quite significant. If you have the terminal object, the bundles over the terminal object is nothing else but the whole category itself, right?
Yes.
It's just isomorphic. And if you take this map, then your pullback, so TE star, as we already observed, is nothing else but product with E, right? Okay. Now what are the points? So firstly you must keep in mind what are the points of one, of A. Well, these are all these split epimorphisms, right? Right?
Yes.
So Tx composed X is identical, right? So if you have a point, the objects in particular have points in the classical sense, right?
Yes.
So the points of A precisely consists of objects which have points in the usual sense. On the other hand, if you look into this, this is the whole of A. Okay? Now, you know that this can be significantly smaller. So this is significantly smaller. How do I write it? Let me write it like this. Although in many cases it may be same, it is significantly smaller, right? Sometimes this could be empty. For instance, if you take locales, it is significantly smaller. or if you take this is empty. There is no object. No frame has a point. Okay? You cannot have a frame homomorphism from the terminal frame, which is a singleton, to a frame. You don't know where to take that singleton, either to 1 or 0. Right?
Yeah.
I shouldn't say it's empty. It has exactly one element. So that is the singleton element. So it is singleton. Okay? So you see this. So looking into points of A is what I'm trying to say is this functor could be successfully restricted to points, the kernel functor. Okay? But the same thing which was here or here, it is not quite possible always to restrict it to points. Okay? So that's the first thing to know. Now in the case when the category is pointed, then we know many more things. The points of well, they are all isomorphic and so on. So not in the pointed case. Now let's see what does it mean. So suppose we are still in the point, consider H still to be pointed. And let me see whether this one reflects isomorphisms. So what is this? This is taking to E cross X. So as I was writing this as 1 or E. This E in the morphism, you know, I mean as the identity map, right?
Okay.
Now, so let's see. So suppose okay. So what does it mean? You have morphisms. Say you have morphism going U0 and you have a morphism going to X U1 such that you have 1 cross F of U0 U1. So that's that map. This is this is identity of E cross Y. So which is saying U0 U1 is identity of E and identity of Y. So which says U0 is identity of E. No, I made a mistake. This is P0 and P1, right? So U0 is P0. This is the U0 is one minute. 1 minute. U0 is so this is one side of the story. 1 minute. This is, I have to be careful. This how do I write this? 1 minute. And you have also the other side of the story. So U0, U1, 1 cross F. This is identity of E cross X. Now let's work it out a little bit. Now what is 1 cross F? 1 cross F, this map. So this is taking P0. Let me write it like this. Okay? Hey, this is a little bit, you have to be careful. That's why. And E cross Y. So let's have some names. This is P1, P1 prime. Say this is P0 and P0 prime. So this one is nothing else but first you go to P1 and then for over here you go to P0 and here you go to X and then move by Y, so it is FP1, and your identity of E cross Y, so it is just P0 prime, P1 prime. Identity of E cross X is P0, P1. So you are saying over here U0 and FU1, this is equal to P0 prime E cross Y, yes, P0 prime and P1 prime, and you are saying over here, so this is U0 of 1 cross F, so which is 1 cross F is this map, so it is U0 1 cross F. I have P, this is P0, and U1 1 cross F is P1, right? So this tells me U0 is P0 and FU1 is P1 prime. Okay?
Yeah.
So now you consider this map. So you take this to be U1 and this one you take the 0 map. So let me be very clear, from Y to E on one hand and the identity of Y on the other hand. Okay? So this is this map H, this composite. Okay? So then we can see that FH is FU1 okay, but FU1 is P1 prime so this is 1Y. So F is starting out, so this tells us that this and HF, if we look into this, so this is U1 So this is U1. Now this is from here your this map is taking Y to E, and let's see. So this is the map X to Y and Y to E. So this is going to be sorry, it's a little bit involved, and this is F. Okay, so this is this map. Okay, now what is this map? This I can write as U1 1 cross F times 1x, but U1 1 cross F is P1. So this becomes 1x. So F becomes an isomorphism also. Okay, it's a little bit complicated. So it shows that in a pointed setup, I needed this pointed setup. So it shows that in a pointed setup, the functor, the change of base functor, so remember this functor, this TE, which is this, so which I was writing, the change of base functor. So let me be careful. Remember, this was also written as 0E, right? This is this, right? Always reflect isomorphisms. So this one always reflect isomorphisms. Okay? Now, no, this is not 0E, this is from E0, sorry. That's from E it is coming. Okay? E0 star. This always reflects isomorphisms. Okay?
Yeah.
Now here is the theorem. Every functor which reflect isomorphisms and preserves finite limits also reflect monomorphisms.
Oh.
Okay? Now, well, I leave it to you to prove this. Okay? The only hint is monomorphisms. A morphism is a monomorphism if and only if its kernel pair is identity, right? Trivial. Yeah?
I can't remember it.
So, you'll use that. And see, so monomorphisms can be represented in terms of certain conditions, its kernel pair is trivial, right? So, which means that the kernel pair is isomorphic to some x and so on. So, reflecting isomorphism and preservation of finite limits, all of these are going to be used to show this result. So, the proof is an exercise. Okay?
Okay.
So if we have if we have what we are saying over here, we are saying something about change of base functor reflects isomorphisms, right? So the change of base functor, remember it is a special case again. It is a special case. This functor is a special case of the pullback functor, right?
Yes.
It's a special case of the pullback functor. So you can see if P star has a left adjoint, right? So you see how things are getting connected. If P star has a left adjoint, then you know that this change of base, you are pretty sure that this change of base will also have a right adjoint, so it would preserve finite limits in particular. So this condition of change of base preserving reflecting isomorphism would also immediately say that change of base reflects monomorphisms, right? Now reflects isomorphisms and reflects, so you see there is a very neat and close connection between reflecting of isomorphisms and reflecting of monomorphisms. Okay? All right. Now, so does this answer your question?
Oh, okay.
Okay. Now
Okay.
let's try to see before we move in for this proof. The proof is a big one, but before we try to, I'm trying to motivate how wide and big and crucial this theorem is. Okay. Now, firstly, take any category A. Look into groups of A or abelian groups of A. All right? So if we have a group, internal group in A, so I'm speaking about groups. These are now groups. Okay, X is a group and Y is a group. And if I take this map, if I take a split, if I take a split and I take the kernel, why do I do this? Why do I do this? No, the kernel would not work. Okay, I wanted to show. I think I didn't do that. I showed that they are unital. In fact, I showed the monoids of A are unital, right? And hence groups and abelian groups are also unital. But I did not show anything more. Okay, I'll come back to it. In fact, the first thing is I'll show that I'll convince you. Okay, I'll do that. I'll convince you. Okay? So, it is not something to do with, so that means I will actually exhibit the last three conditions are going to hold for these categories. Okay? Now that is D, E, F, any one of them I shall show. Now the fact is, this first tells you that the notion of protomodularity is so much, how do I say, in abundance. Okay? You take any category whatsoever, and your internal groups or internal abelian groups, they are all protomodular. So for instance, you have such a kind of a diagram. This 2 out of 3 law holds for them, right? So firstly, this once I show this, you will be given this, you should be now convinced that the notion of protomodularity is quite important, right?
Yes.
Because if something happens so very frequently, then it is surely to be investigated in its own. Okay?
Yeah, but by protomodular, do we mean pointed protomodular?
Yes. Sorry. So any pointed category is said to be protomodular or pointed protomodular if it satisfies any one of these 6 conditions. And if it is not pointed, so let me write it. Pointed protomodular is any of these 6 conditions. And just protomodular any of D, E, F. Okay? So you see this kind of an example tells you how common or how significant this notion is. Okay? Now, suppose So this is another theorem. If say F,
So even if A is not pointed, but the category of internal groups of A can be pointed, is pointed.
for the case of sets, yes, it is. But let's try and let's try and take this subcategory. You take the subcategory of sets with at least 2 points, 2 elements, the full subcategory. All right? This doesn't have a terminal object. And what are the groups? The internal groups are just then sets with the group structure, right? But the only fact is that the group there is at least. So it is essentially the groups with at least 2 elements, right? So you don't have a. So it's not pointed. It doesn't have a terminal object.
Oh, okay.
Right?
Yeah.
So it is the fact that groups is pointed depends on the fact that now you therefore therefore you can see that so it's a question whether if you take sets of containing only at least 2 elements, you take the forgetful functor, take any set with at least 2 elements, then you also have the free group. So everything that you knew about groups, the free group, the generators, relations, everything works as though nothing had changed. But the only difference now is you don't have the category to be pointed. Right? So it is not abelian. Right?
Okay.
There are so how do you say that something, so this theorem therefore fails when you say that a group homomorphism is a monomorphism if and only if its kernel is a singleton. Right? So the kernel of a group, remember the kernel, how difficult it is becoming. The kernel, or let's say the subgroups even. So subgroups in this category are all those subgroups which have at least 2 points. So for instance, if you take an injective map and look at the members which are taken to 1, so that means you are looking into the kernel is no more a subgroup. Right? So you see the point. These theorems are going to fail. Okay? But still you can speak about several other properties of a group. So what is it that you can, so do you see that we are going to target certain properties of groups which are just not dependent, say, on the number of elements or such things intrinsic of the set. So it is essentially certain categorical properties of groups that we are interested in. You see the little difference, and the very subtle difference between properties of a group and categorical properties of a group. Saying that a group homomorphism is a monomorphism if and only if its kernel is singleton, is 0, right?
Yeah.
This is not true if you are in this kind of a category where you don't have the smallest group, the terminal group. Yeah? So that's the problem. We are not interested. So this is a property of groups. Yes, it's a property of groups over sets or over a pointed category or what. Okay. There it is true. But it is not a categorical property. A categorical property of groups would be those which would hold anywhere, right? In any category of groups. So that is what that's what we are trying to focus on. Okay? And the consequences of that. So group and group-like properties, it means categorical group and group-like properties. Group and group-like categorical properties are the ones that we are interested in. Not group and group-like properties only. Okay? Because there can be some properties which hold in some special cases, but it doesn't hold for others. Do you see this? Okay. The next one that I wanted to say is, suppose if this is a functor this is a functor which reflects, which preserves finite, which reflects isomorphisms and preserve finite limits. Let me not write this as finite limits. Then A is protomodular. B is protomodular. Okay? So, well, I again, so in particular, if you have a functor which is reflecting isomorphism and has a left adjoint, okay, then protomodularity of this would then imply protomodularity of B, right? Okay. So hence consider this. I know this has a left adjoint. Right? So therefore, commutative rings is protomodular. And this reflects 0. Reflects iso. Right? If you have a ring homomorphism such that the corresponding abelian group homomorphism is an isomorphism, then the ring homomorphism is automatically an isomorphism, right?
Okay.
So you know that this is the case. Commutative rings is a so commutative rings is protomodular. Protomodular. This is the reason. Okay?
Okay.
Can you tell me another one? So, if you have this, one minute.
Get to set.
1 minute, 1 minute. Suppose if you take the K is a commutative ring, and you take this one, you form the group ring. Okay? That's the left adjoint. So that also says K algebras are protomodular. Okay?
Okay. And get to set.
Okay, let's see. Get to sets. What is the functor?
It's set. Okay, we can call it discrete functor.
Okay. So you just forget. You just take the vertices.
Yes.
Right? You set of objects.
Yes.
And you put the discrete. Okay? But set is not protomodular.
Oh.
This is the issue. Okay?
Okay.
Think of another. Okay, I'll leave it to you both of you.
Okay.
To use this and find other examples. Interestingly, I would be interested in your conclusions about frames. Interesting about, say, distributive lattices or, say, bounded lattices. So the ones that you have come across. Okay?
Okay.
So that's what I would like you to look into. And uh, then obviously we have also seen that uh, if you have this functor, mm, this okay, we will see this next time. Yeah. So the next time we will now give a proof, but before, okay, first let me give a proof of this, but also I would need to give you a convincing proof of this fact that these two are protomodular. Okay, and then we will give a, so that's what we will do next time, as well as I'll give a proof of the main theorem. Okay.
Okay.
Yeah.
I to the coach.
Yes.
Did you record?
Yes, I recorded.
Oh, okay.
Okay, because my screen. I don't know. I keep on losing the screen time and again. So
Okay.
I'm not actually seeing what you're writing.
Okay.
So I don't know. Maybe we have to go back to gist again. I don't know. Because last week also it was a similar thing. It keeps on switching off the screen and switching on, switching off. I don't know what's the problem.
Okay.
Yeah.
Okay. I have recorded, yes.
Okay. All right.
Okay.